All right, today we're cracking open a book that really kind of quietly built the instruction manual for modern science. It's called The Principles of Science by William Stanley Jevons, and it's all about how we figured out how to turn a bunch of random facts into knowledge we can actually rely on. So, let's get into it.
But let's start with a question that feels like it could have been asked yesterday. Could a machine actually think? This wasn't some sci-fi prompt. It was a serious obsession for our guy, the 19th century logician W.S. Jevons. He was so convinced it was possible that he went ahead and actually built a logical machine, which was basically a mechanical computer made to solve logic problems. But this quest to understand reasoning, it wasn't just a pet project. It was his response to a massive crisis that was happening in the world of science.
So picture the mid-1800s. It was this absolutely explosive time for discovery. Scientists were finding new species, new chemicals, new forces of nature. Data was just pouring in from all over the world. But there was a huge problem. As Jevons himself put it, all this rapid progress in science wasn't matched by any progress in the theory of reasoning itself. In other words, they had mountains and mountains of facts, but their method for making sense of it all was deeply, deeply flawed.
See, the main way of doing science back then came from Francis Bacon, and it was pretty simple. You just go out, collect as many facts as you can, and eventually some general law is supposed to just emerge. But as the world of data got bigger and bigger, a fatal flaw in this plan became super obvious. How do you know which facts to collect when there's an infinite number of them out there? You can't observe everything. This passive approach was completely breaking down. Science needed to get active.
This huge challenge actually has a name. It's called induction. It's the whole puzzle of how you make that leap from a few specific things you see, like a single apple falling, to a universal law, like gravity. For centuries, this was a huge headache for philosophers. The whole process just seemed more like a mysterious art form than a repeatable science.
And this is exactly where William Stanley Jevons walks onto the scene. He's armed with this shockingly simple, totally revolutionary idea. He basically said that everybody was looking at the problem from the completely wrong direction.
So here it is, Jevons' huge insight. Induction isn't some mystical, separate thing. It's just deduction, but flipped on its head. Instead of just passively waiting for a law to show up in your data, you have to actively propose a law. You make a hypothesis. Then, you use good old-fashioned deduction to figure out what else must be true if your hypothesis is correct. And then you go and test those predictions against reality.
He just collapsed the two ideas into one incredibly powerful process. The goal wasn't to invent some totally new kind of logic. It was just to use the logic we already had, deduction, but in a new, creative, and predictive way.
And this single insight builds directly into the playbook that, pretty much all of science still uses today. Jevons wasn't just pulling this out of thin air. He was describing the method that the most successful scientists were already using, even if they couldn't really explain why it worked.
And here it is, the 4 steps that power modern science. First, you observe something interesting. Then, you make an educated guess, a bold hypothesis, to try and explain it. That's the creative leap. But then comes the tough part. You use deductive logic to predict what other things have to happen if your hypothesis is right. And finally, the most important step of all, you design an experiment to see if your predictions actually check out. It's this active, creative cycle that's always correcting itself.
Jevons actually called this the Newtonian method. He argued that Newton didn't just stumble upon gravity by collecting a bunch of falling apples. No, he hypothesized a huge, universal law, and then he spent years deducing all its consequences and checking them against astronomical data. That, Jevons said, was the real engine of discovery.
But there's a catch. If our knowledge just comes from testing hypotheses, how can we ever be totally sure that a hypothesis is actually true? Well, this brings us to the second massive pillar of Jevons' system, probability.
Jevons used this brilliant analogy to make this all make sense. He said to imagine that nature is like an infinite ballot box. We can never see all the ballots inside, so we can't know for sure what's in there. All science can do is reach in and draw out some samples. That's what experiments are. And then use those samples to make a probable guess about what's in the rest of the box. And the crucial point here, because the box is infinite, you can never draw all the ballots, which means you can never ever get to 100% certainty.
So, for Jevons, every single scientific law is really just a statement of probability. Newton's law of gravity isn't some absolute truth etched in stone. It's a hypothesis with an overwhelmingly high probability of being correct, because every test we've ever thrown at it has confirmed it. Science isn't a quest for certainty. It's a process of just getting better and better at calculating the probability.
And this whole probabilistic view of science leads to a really profound, and for a lot of people, a deeply unsettling conclusion about the very limits of what we can know.
And here is the big twist. The very idea of an unbreakable reign of law in nature is itself just another hypothesis that we can never fully prove. That feeling of certainty we often have about science is, as Jevons put it, largely a delusion. Now, this doesn't make science useless. It's incredibly powerful. But it does mean that its foundations are built on probability, not on absolute, unshakable certainty.
So what's Jevons' lasting legacy? Well, it is immense. His hypothesis-driven method is literally the blueprint for all of modern science. His work is what cemented the role of statistics and probability in all research, and maybe most importantly, he gave us a clear, a humble, and a really powerful way of understanding what science actually is. A process for getting our probabilities right, not for declaring absolute truths.
And that leaves us with one final, fascinating question that Jevons just forces us to confront. If the very foundation of our most rigorous way of knowing things is probability, not certainty, what does that say about the limits of human knowledge itself? What, if anything, can we really ever know for sure?
This is for entertainment and educational purposes only.